Okay, I'm Michael Vanter from Oracle Labs, and I'm associated with the VM Research Group. I've been working with that group for a number of years. And it's nice to be here today. It's really a great opportunity for me because I'm feeling like one of those, outside speakers you invite to sort of conferences, somebody who comes in from totally left field to tell you something you'd never heard before. And so that's my job today, is sort of being a speaker for tools. That's what I do. I'm the one person in this group that pays 100% of my attention to tools. And in particular, working with the language implementation community, sort of the VM Research Group, is sort of a great area. I see my interests in tools are really very much focused on things that people use, programmers use. And in that sense, I see myself as kind of a UI guy. So in my worldview, I actually build the user interfaces for your technology, right? Because most programmers don't see your technology. What they see is tools. They see editors, they see debuggers, and all that kind of stuff. So that's my point of view, and I just wanted to make that clear. Now, some of my best friends are implementers, so it's actually cool. I'm cool with that. But I really always take this point of view that tools that programmers see is really where I want to put my attention. Okay, so having said that, here's the topic for today. It's debugging at full speed. This is the name of a paper we delivered recently at the Dynamic Languages Symposium. But in fact, that's not really what the talk is about. I kind of lied. It's really not so much about debugging as it is about instrumentation. And in particular, instrumentation in the context of the Truffle framework. Now, you probably heard that mentioned Monday when Charlie Nutter gave his talk, because there's a Truffle implementation of Ruby that's now sort of a branch in JRuby. How many people have seen talks about Truffle? I'm just kind of curious. So it's pretty familiar, so I won't have to spend too much time on that. And this is really good. So the thing I want to talk today about is instrumenting Truffle implemented programs and why I might want to do that. And as I go through the talk, which is going to be about some of the nuts and bolts, I'd like you to listen for two particular themes that are sort of a little bit bigger. The first one is, which is where I live, which is the notion that the language implementation technology, the goals you have and the goals that external tools have, aren't exactly always well aligned or consistent. Okay, there is a creative tension that shows up when you want to build a debugger, and versus sort of the compilers, the runtimes, and all that kind of stuff. And that's what makes my work in the VM Research Group pretty interesting. There's an even bigger theme to listen for, and that's what happens when you swap out a core-based technology. So the Truffle Growl platform is really quite a bit different than the traditional ways languages get implemented. And one of the things we're seeing is how that ripples out and creates new challenges and opportunities around it. And that's certainly the case in debugging and in instrumentation in general. So with that, let's go. So I am obliged to tell you that I won't lie, but you shouldn't trust anything I say anyway, the usual. Okay, what's the big idea here? There's two things. First of all, observe what's important about the Truffle platform. Now, this is my perspective as a tool builder, and what I see is what a great opportunity to see how you can build pretty well-performing implementations of these languages, the dynamic languages, that's our target, with a fair bit less implementation effort than it would take for a high-performing handwritten implementation. So that's pretty cool. So what about the tools? Okay. What I want to do is play the same game. I want to build support for tools into the Truffle platform so that you can actually have access to the execution state, build a variety of external tools, including debuggers, that plays well, doesn't have a lot of overhead, and also doesn't have a huge implementation burden. So the idea would be that if you implement your language in Truffle, then with a certain amount of extra effort, you might actually be able to get a running debugger for it, or perhaps some other tools. So that's the big thing that's going on. So here's what I'm going to talk about. I'm going to sort of review Truffle a little bit, although fairly briefly, so that we can get on to the other stuff. If you want to ask deeper questions about Truffle, we can talk about that later. Okay. And I should also disclaim, not being one of those implementation guys, I don't actually know this technology quite as deeply as some of the other people, but luckily there are some people in the room who do understand that. Yes, and they're back there. So ask later if I seem to be unclear on something important. So the key idea about Truffle starts with the fact that the implementer writes an AST interpreter, the sort of thing you probably did in a graduate compiler course. And then does the first sort of line of optimization for dynamic languages, and that's type specialization. And it does that by the ASTs rewriting themselves. And so there's a technology for that. So the tree specializes. In this case, we have some uninitialized nodes for addition that gets replaced by integers. And those then can compile down in a sort of successive optimizations of partial evaluation and aggressive compilation inlining, turns into a very efficient binary. And that's sort of the Truffle in a nutshell. And the assumptions behind that specialization are then guarded by some very, very efficient triggers. They're called assumptions. And then the other important thing about it is that the platform can de-optimize. So as a debugger person, what I'm interested in, can I get to the execution state? The good news is I didn't have to actually do that work myself. The platform comes with a full de-optimization technology that restores the execution state, which is how the system works when it needs to sort of invalidate one of those specialization assumptions or something else. So this is great. Here's what we get. We get sort of, anytime I need to, I can kick the tire, cause a deopt, and I get the full execution state. This is really good news for me, okay? So here again, the last thing I'm going to say about this, the whole architecture of this, you'll see that there's a Truffle API, that's the second layer down, the framework for node rewriting. And in that general area is where I want to see some extensions. Okay, so again, what is it about tools in this platform that makes sense? So again, I've already alluded to the key one, which is that we can actually gain access to the Truffle runtime. And here's the first reason why. The first reason is that the interpreter is all written in Java, and it's an interpreter, so we know what that looks like. And the execution state is explicitly represented. I mean, there's objects for the stacks and frames, everything you want to know. It's all right there. And you can then write Java code to get access to that execution state. And if you've ever implemented a native debugger, sort of imagine how that compares to sort of scraping bits and trying to reconstruct as much of the optimized execution state as you can. It's a dodgy business. The other opportunity is that, as I've mentioned, the de-optimization. This is really great. So we can get very high performance, but when we need to, we can reconstruct the execution state, and the tool builder doesn't have to worry about that. So what's the challenge? Well, it's a new technology, so how do we play together with that? The idea is to follow the Truffle lead and build as much into the platform that's language agnostic as possible, but at the same time, not getting in the way. So we don't want to disrupt any of the ordinary Truffle operation. At the same time, we want to benefit from Truffle, and in particular, we want our instrumentation to be fully optimized using the Truffle optimization technology. So there's a dance there, and that's really where a lot of the early work in this particular project took. It took quite a long time to sort of get my head wrapped around this and figure out how to play in this world and dance this dance. And then, once the way is clear, then what I want is an API for tool clients, and I want it to be really simple, easily accessible, all Java, so you can build some tools. So, what's the key strategy? The strategy we finally landed on was this idea of just adding extra nodes into the tree. And these are, we call them wrappers. It's an old idea. It's not particularly new at all. For us, adding one of these wrappers in is a way of creating a point where the program can be instrumented. And that's how we do it. That way we have our own classes, the wrapper class, and a bunch of other stuff that works with it. And we don't require that any of the implementation classes in your language implementation be modified, at least for the generic kind of ordinary, simple, low-hanging fruit kind of stuff, which is kind of where we are now. So far, so good. Again, the wrappers are designed to be transparent, both in terms of the execution semantics of the language you're implementing, but also in terms of performance, and that's really the critical thing. So the optimization technology in Truffle and Growl is so good that if we play our cards right, all our overhead goes away until we're actually doing something important. They're composable. We'll see how that looks. And the last disclaimer is that the class of tools I'm building at the moment are focused on issues at the language execution level. So imagine sort of a Python debugger. It's really all about Python. It's not about memory layout. It's not about a lot of low-level stuff. So it's not really I'm not planning to build tools for the people who implement these languages so much, although there's a little bleed over there. Mostly the idea is to build a debugger for somebody programming in the language you've written. Okay, on to what happened. I mentioned that we finally settled on this wrapper strategy. How did we know that that strategy was going to succeed? And this work was done in collaboration with Chris Seaton, who was an intern in our group last year, who took on using Truffle to implement Ruby and did miraculous things. And along the way, he got very interested in the work I was doing, and we talked a lot about that. And finally, he decided to give this wrapper strategy a try in his implementation that he'd been working. And so he put together something pretty interesting. And why debuggers? Well, okay, debuggers is sort of the classically hard problem. So we picked that one first. It's very important. Everybody wants one. They're hard to build. And that's exactly the problem. They're hard to build. They're hard to build for a variety of reasons. I'll mention a few here, but they tend to be tightly coupled to the sort of the native level of whatever you're doing. And that's expensive. They often sort of cross abstraction boundaries in the architecture of your implementations. They sort of require access to things that the implementers don't always want to bother to create access to. They often require that the implementation preserve more execution state than they really want to for performance. So it's a world of hurt trying to implement debuggers. That's why we don't see very many good ones. And for the programmer, there's also some trade-offs associated with debuggers as conventionally written. And I've just mentioned a few of them here, right? There's usually some cost to your debugger, sometimes in more than one of these 4 categories. So there's performance, features might not be supported, it's tough to get the implementation requirements supported, and you may not be able to actually run debugging services in the actual environment that you're deploying your program. So that's why debuggers sort of looks like a good place to start. So here's just a brief view. Everybody here probably knows what it looks like to add a wrapper node to an AST. Here's sort of a sketch of a Truffle-looking AST-ish thing for a piece of code. And what is a wrapper? Well, here's a case where we've stuck in a wrapper around each statement, let's say. Again, semantically transparent, compiles away. It's just a placeholder where you can do something. So that's just the key concept there. In his prototype, Chris then built into the language. So he created some built-ins to do this in a particular kind of wrapper. So let's look at this example here. That little concentric circle there on that one node is meant to represent a wrapper node he stuck in that implemented something, let's call it a breakpoint. And at the moment, it's not active, so it has sort of a state bit that says it's not active. And that state bit is sort of been annotated to suggest to the compiler that it should be treated as constant for the purposes of partial evaluation, at which point then it gets compiled away. There's actually no remaining code for it other than a guard. And the guard actually relates to the assumption, and the assumption that is created says there is no breakpoint there. And it's constructed so that if you come in through an API, in his case, by extending the language, again, it's built into Ruby, you invalidate that assumption, that causes a deopt. And at that point, the node and his implementation strategy then was to swap, the node would replace itself in the tree. Remember, that's what Truffle does. It does kind of node replacement. A active breakpoint node gets replaced into the spot that the inactive breakpoint was there. And a new assumption is created that says there is a breakpoint at this location. And then you proceed, and if you run for a while with that breakpoint there, pretty soon it'll get compiled as well, and you'll end up with a very efficient binary that has no more code than necessary to sort of interrupt the flow of control and call out somewhere. So, any questions about that, just for clarification? Does that strategy kind of make sense? This is really the core thing that we do with this framework, okay? Okay, so interestingly, Ruby has a language feature called setTraceFunction, which allows you to create an arbitrary proc in the Ruby sense and attach it and say, run this proc just before every single line of the program execution, go. It's notably a hard thing. Charlie Nutter mentioned it on his list of really hard things to do about Ruby on his Monday morning talk. And it's famously difficult. For us, it works pretty well because what we can do is we can put an inactive trace node in front of every statement. And they're all, in his implementation, they're all tied to one assumption, which is that we're not tracing. And sure enough, when everything gets compiled, there's no trace of those nodes left. They're gone. There's no runtime overhead once it's compiled down to the fast path. Okay. And then when you decide you want to turn tracing on, the assumption is invalidated. And now lazily, not eagerly, if that assumption is invalidated, every one of those trace nodes, the inactive trace nodes, will check to see if its assumption has been invalidated. If so, it will deopt, replace itself with an active trace node. It will connect to the proc. And you will end up, once the whole program is executed, something that looks like this. And then if this runs for a while, eventually it will get compiled back into the fast path, and everything will run at full optimized speed. So that's actually a fairly promising way to implement set trace function in Ruby, and it's fairly unusual, as we'll see. He also built some ordinary debugging functions, again, as sort of built-ins into Ruby, so that you could just talk to the shell and you could type in things. So you could write little commands like this. So there's a breakpoint. You can write a command that says break. You can just put that in your code, and it'll cause a break. And the one at the bottom is a conditional breakpoint that also has a little proc that runs. And again, this is all very Ruby-ish, and it just leverages sort of the instrumentation sort of strategy pretty well. Okay, so evaluation. So in this paper, which I cite at the bottom here, that was just presented at the Dynamic Language Symposium, we reported the results that Chris got for this work with the debugger and with Ruby in general. And just as a background, before we talk about the result of the strategies, it's worth noting that across the implementations of Ruby, there's actually quite a bit of variation in their raw performance. So the evaluation we're going to do are normalized to each one's implementation, and you'll see that. But here it's important to notice that on these two particular benchmarks, the variation is quite extreme. JRuby plus Truffle is the rightmost one, and that's the branch of the JRuby repository right now that has the Truffle execution engine as a backend in it. And you'll notice that JRuby without Truffle is also listed there. So you can kind of see that there's a large relative base performance before we even start what we're doing. But the goal of the paper was to look at the overhead that we add with our instrumentation framework. So let's have a look at that. So here, this is a kind of a linear scale, and bigger is better. This is actually a log scale, and smaller is better. So this is an overhead comparison. And you'll see then that we're comparing the five implementations of Ruby, and across the bottom are some different things that you might do in the space of tooling, starting with just turning on the trace function, not actually adding a proc, but just saying, I want to make it possible for us to do trace functions now. Some of them don't do that. There's no implementation that does it. So you'll see that Rubinius, for example, doesn't support that. So there's an NA there. And it's hard to see the JRuby plus Truffle one because in this case, it's essentially constant. There's essentially zero overhead. So you have to actually put a little annotation there so you can see it on the chart. So you'll see that JRuby's strategy for implementing trace function takes a pretty good hit when you sort of turn it on. But then if you actually use it, notice that JRuby sort of gets more expensive, but Topaz, which in general is a pretty high-performing system, really takes a dive. Okay, it's really bad. Like more than 3 orders of magnitude. It's a fantastical difference. And again, that's testament to the fact that it's hard to implement using the traditional technologies. Again, so you'll see that the JRuby plus Truffle has the least performance hit of any of the systems that actually implement set trace function at all. Going across, you'll see that just turning on the debugger for the ones that have debuggers has no cost in JRuby plus Truffle for the reasons you just saw. Breakpoints, kind of the same thing. It really doesn't, asymptotically has essentially no overhead. And then when you get to conditional breakpoints, again, you see various trade-offs among the different implementations. But in every case, the JRuby Truffle version sort of is pretty modest compared to everything else. So we're really pretty excited about these numbers. This really told us that, yes, we were on the right track. We could do instrumentation across a wide variety of applications and play very well with Truffle. Okay, so onward to how to generalize this. Okay, so the Ruby built-in was a pretty interesting experiment, but it really falls far short of what we're looking for in the area of instrumentation in general. So the prototype, for example, was built into the language. Well, we want to have the option to do language agnostic tools, so an external debugger, for example, that isn't built into the language, but works more like a conventional debugger, not in a conversational shell. So you should have the option. And that has the advantage that there can be a lot of shared code that doesn't have to be added by the language implementer. So again, part of the game is, can we get you a debugger without requiring that you, the language implementer, do a lot of extra coding? So we want an API for tools that's pretty much language agnostic that provides those shared services. Second of all, the prototype strategy was to build a wrapper with a specific function. So I mentioned there was a trace wrapper, an inactive and an active. There was a breakpoint wrapper, an inactive and active. For our purposes, we want a general purpose wrapper. The idea being that you, the language implementer, have to implement the wrapper because it has to pass through your execution semantics. But all we require, as far as if possible, is that you only write one of them. that can be put anywhere in your trees, and then we do the rest in the framework. So general purpose wrapper, we hope only one implementation class. Notice also that if you were setting a breakpoint in the prototype and there was also a trace there because it's out of line, there's going to be two wrappers. So they compose semantically, but it's kind of awkward, and it requires now that you implement more wrappers that have language-specific aspects. So rather than multiple wrappers, again, we have the single wrapper per location, and then that delegates out to a bunch of code that's generally pretty much language agnostic. And we'll see some examples in the API. So again, we get a lot more generality that way. So if you put a wrapper there that says you can instrument here, everything else is potentially language independent. The wrappers have to be added statically in the current implementation, and that's a real constraint. When you're building the AST, you have to put the wrappers in. We don't have technology for adding wrappers to ASTs under execution. So that's also a problem if you have a function-specific wrapper. If you want to make potential breakpoints, you have to decide up front. What we want is to be able to dynamically add tool functions, potentially from many tools simultaneously. So we want that to be as dynamic as possible. Okay, so that's also a shift there as well. And finally, the strategy that Chris used in that prototype where an inactive and an active node swaps itself out is a perfectly fine thing to do and very much in keeping with Truffle and Truffle think. But it turns out not to generalize really well, again, if you want to make it easy for the language implementers. So what we want is the tool functions or the tool people to say, well, I can actually play the same game by changing the state of the stuff that I stick in there, and you will see a slight example of what that looks like. So these are areas where we want to build out something way more general and scalable along that same line. But again, the core performance issue has been resolved, and we're sort of ready to go. Okay, so there's really conceptually two APIs here. There's an API for the language implementer, which at the moment is kind of fuzzy, and the reason it's fuzzy is that we're really only getting started with it. And I'll talk about that for just a moment here, and then I'll also talk about the tool client API, which I think is personally more interesting. But as a language implementer, what do you have to do? Well, I already alluded to the fact you have to build one of these wrappers that is semantically transparent and can be put at all the places in your program where you might want to do instrumentation. So there's a requirement. And in particular, you have to use some mechanism to modify the AST by sticking those wrappers in at any place where any tool might want to add instrumentation. Here's an area where I mentioned creative tension between language implementers and tool people. Generally, compiler people don't like to bother with source attribution. In other words, tracking exactly what text corresponds to which node in the tree. It's a pain to get it right. It's a pain to make it complete. It takes up space. If you're building these kind of tools, you have to have it. It's a requirement. The reason it's a requirement is that, and now I'll put my UI hat on, a tool cannot communicate with a user without being able to describe the piece of the program you're talking about. Users deal only with concrete syntax. Users do not think about abstract syntax or anything else. Okay, this is a well-established fact. So you have to be able to create that relationship in any tool that comes along and say, oh yes, I'm talking about this particular expression and it goes from this character to that character or this block or whatever, and that has to include the braces. And when was the last time you saw any compiler error remember where the braces are? Generally does not happen. So creative tension, it's a big hassle, but if you want tools I win, you have to do it. And finally, there's additional stuff that is going to need for the kind of tool you're doing. So for example, in debug, you always want an eval. So as a language implementer, if you want that to work in your debugger, you have to provide some implementation for that hook that says, yeah, how do you do an eval? That's the one example that sort of we're working on now. There will be more as we build out the debugger to add more functionality. It's unknown territory, so we're still figuring it out. So that's what you as a language implementer have to do. If you're a tool builder, here are the kinds of things you want to think about. These are the concepts of the tool API. I already mentioned source attribution, so that's a class we call source section. It's very precise. This character to that character corresponds to this node. And in particular, that node has to correspond to something that makes sense to a user. Otherwise, the tool is of not great use to the user. If you can't talk about what you're talking about in terms of concrete syntax, you can't talk about it usefully. So source section is an implementation technique for that. Second one is even more interesting. It's called a syntax tag. This is an arbitrary annotation, sort of a symbol that you can attach as a tool builder. You can actually make decisions about attaching these tags, and they're there to configure how tools operate. It's how, for example, a tool builder or a language implementer would say, for this language, here's are the things I want you to consider statements. Okay, I'm going to put an instrumentation point there, and I'm going to put a tag there that says, treat this like a statement. If you say that, then our debugger will know what to do. It'll stop there. And you don't have to write language-specific code for it. The idea behind having the tags is to separate the concerns about how you build your AST and how you want users to think about it. Okay? You should understand this node as an expression. You should understand this node as a statement. You should understand this node as a call. You shouldn't know about this node. There's no tag. Because it makes no sense. It wouldn't help. Okay? So then we have this notion of execution event, and this really goes back to the AST interpreter model, where execution flows down the tree and back up, and all our instrumentation framework does is it provides a hook where you can sort of say, oh, execution just entered this wrapper, and oh, by the way, yeah, the child just returned, and here is the return value. So that's the space of execution events. Very, very simple, and in general, language independent. The instrument is where we actually get work done. This is an API for the thing that you could insert in the program that could receive those events and do something you care about. And there is no specialization. You get the events, you do whatever you want, it's all Java. Okay? We'll see the actual API for that. And finally, there's a thing called a probe, and the probe is what connects the dots. A probe is the representation of a location in the program where you can manage things like tags and instruments. The probe is sort of designed around the metaphor of electronics, if you're ever into that sort of thing, where you got a circuit and you want to hook a probe to it, and you say, okay, I want to tap into the circuit right here, and I might want to hook this to it or that to it, sort of whatever those instruments are. So being driven here by the metaphor of probing into that kind of a system. Why is a probe separate from a wrapper? The reason a probe is separate from a wrapper is that in the Truffle execution model, ASTs once built are cloned often. And if you clone them, you really want the same instrumentation at each site. So you're going to have a wrapper in each one of those clones. They're going to share the probe that is associated with that location. Okay? So that's the universe of these things. Once I've said that, the APIs look pretty straightforward. Here's the abstract instrument class. It has a method called enter, which you can override. And it says that we just entered this node, or about to, and you get the node and you get the frame. With that information, you can pretty much find out what you need to know. You can write code that looks around in the tree if you know how the Truffle stuff works. And they're still working on APIs, so there's a stack API that's sort of being refined. And that's it, that's all you need, okay? Likewise for leaving, there's sort of the void leave. And then there's some other leaving methods that relate to what the return value is if you care. If you're in the kind of language like Ruby where all returns are basically boxed objects, then all you need to do is really that third method, node frame, returning, and here was the real result was an object. There's an option if your language implementations are more aggressive and deal with unboxed return values for efficiency, which is important in a lot of languages, then we also have leaving methods for all the primitives, and the default implementation is to box them for you. So if you don't care about the performance hit in your debugger, then all you have to do is implement the third method for return values if that's what you're looking at. But if you really want code that's not going to disrupt the optimization and there are primitives, then you're going to override those others. But that's pretty much it. There's basically one method for every possible return type, object, primitives, and then there's the exceptional one. And that's it. You write the hooks. That's all you need to know. So that's the API. That's the whole API for what an instrument is. What's a probe? I already mentioned that that's really the manager. So a probe it's associated with a source location. You can add instruments and remove them, and you can add a tag. And the tags are open-ended. Any tool can add a tag, and that configures kind of all your machinery. There are sort of support methods. You can add a listener that if you want to sort of watch probes as they're being created in a particular language, you can do that, and you can sort of look for certain tags. So the debugger, for example, watches for probes tagged as statements, and then it puts them in a table. That's how it knows where all the breakpoints can be put. Okay, that's the sort of thing. So that's pretty much it for the probe. And also there's some methods for going and finding probes if you didn't already map them out. And you can basically scan for them either by line number or by the tags, that sort of thing. So, and that's pretty much it. That's the public API for tools on top of Truffle. So again, it plays with Truffle. If you want to do anything non-trivial in those implementations, you're going to need to know something about Truffle as a tool builder, but you mostly don't have to deal with too many language-specific things if you don't want to. So where is this being used? Well, I already mentioned the Ruby implementation. Right now, all the Truffle Ruby work is being done in the JRuby repository now. I already mentioned set trace function, where we've got really fabulous numbers there. And I talk to Chris pretty often. He recently did an implementation of the object space stuff, which is pretty challenging, but he discovered that it really wasn't too terribly hard in our world, so he built a visitor for traversing objects and stuff. The interesting thing about that was, though, that for that to work, he felt he needed to stop all the threads in the core library, and he didn't have a way to do that. And he thought about it for a while and thought it was going to be hard, and then finally he figured out a way to do it with instruments. So he basically puts instruments at method entries and at loop entries that check the assumption, and that's the efficient way we stop threads in that particular language. And he said once he figured it out, he basically did thread quiescence in a half an hour. So again, validates sort of the generality of the framework and the power of the underlying Truffle system with those assumptions that you can create. Okay, simple profiling. One of our collaborators working on the Python implementation at Irvine is starting to use the instrumentation framework for finding hotspots. This is done, again, at the language level, at the Python level, so counting invocations, not low-level memory kinds of stuff. But one of the things that has come up is how to record sort of slightly more complex information. If you want, you can just count things at nodes. And the answer is, well, your instruments can get arbitrarily complex. So for example, you might actually have instruments that build a table on the side of some information you're gathering. So you want to gather some summary statistics, and they may be context dependent. So your instrument may say, is there a particular call on the stack somewhere above me? If so, count it, otherwise don't. There's all sorts of contextual information that you have available. And so she's slowly working into that as she's building up her ability to kind of monitor the executing Python programs. Okay, now I'm finally going to talk about debugging. So what we have right now in the more general framework is a limited, pretty simple debugger. And the first thing is what I call a debugging engine. It's not a debugger, it's just the thing that knows how to do debugging type stuff. And it does breakpoints, it can step in, over, and out. You can actually list the variables in the current frame where you stopped. There's a backtrace. Interestingly enough, you can evaluate a string in the context where you're stopped. It doesn't hurt a bit that these are dynamic languages that usually have a built-in eval command already. So we have a real head start. So it turns out in this world, it's actually not very hard for your debugger to do an eval. And so far, again, we're sort of doing low-hanging fruit. Almost all the code in the debugger engine is language agnostic. And then when you want to bind it to a specific language, you have to add some extra stuff. I already mentioned things like eval. And we have that debugger engine actually up and running for both Ruby and JavaScript at equivalent levels of functionality. It does all the things that I've listed there. We've just started in on R, which is a whole other game. It's quite a bit more complicated. My intern is working right now on Simple. That's our demonstration language. It's in the public API. Demonstrates how you implement a language, a relatively simple language in Truffle. So one of the things we want to do is to document and demonstrate how then you would add the code you needed to actually have a debugger for that language. So this will be going out. So kind of that's where we are in the space of language-specific adaptation. I mentioned we would look at what an instrument might look like. This is the breakpoint class. Well, it's the implementation of the breakpoint class. There's some machinery around it. It extends debug instrument, which extends instrument. You already saw that API. That's the abstract class. It has a Boolean that says whether it's enabled. That Boolean is annotated in such a way that Truffle will treat it as constant when it does partial evaluation until we tell it otherwise. So this is a way we can manage that sort of thing. So this is the state change idea. So if we mark something as compilation final, then we have the responsibility of not changing it without kicking the tire so that we know something has changed. And basically, you give it a callback, which is your debugging engine, and on any enter, this particular breakpoint says, am I enabled? Okay, call halt. Okay, that's it. That's how breakpoint instrumentation works. That's how we have inserted a breakpoint into the flow of execution. And most of our instruments so far look very similar, very simple. Okay. So that's just the engine. What else do we have? Well, I've implemented a command line debugger, an actual debugger tool for demonstrations and testing. And it actually works. It does all those functions. It kind of has a funky command set that looks a lot like the old GDB command line debuggers. The interesting thing is I kind of have a quasi-client server architecture just to keep as much separation as possible, so it uses message passing mostly to communicate with the server. The server is language specific. The client is language agnostic, actually. It connects to the same code, can then debug Ruby or JavaScript right now. And it pretty much works. You've got this command line debugger, and you can sort of do debugging kinds of things with it. And for anybody who wants to sort of have a look at that or ask hard questions, we'll be doing a workshop right after this, and you can come hang out and we'll look at it. And finally, sort of, we're also curious of what it would look like to integrate this technology with an IDE. So there's kind of this sort of back burner experiment that says, well, what would it take to sort of connect these things together? That's not very far along, but it's an interesting idea. But again, it sort of says, how do we build real tools? And if you're going to build real tools, you have to hook up into the IDE ecosystems. So that's pretty much it. That's what instrumentation in Truffle looks like going forward. There's a lot of opportunity for building new and interesting tools, which is what I hope to do once I get out from under the debugger. Debuggers, even the simple ones, are still kind of a pain, and I think there's a lot of opportunity to instrumentation to do stuff we haven't thought of yet. And I think it's also interesting to explore the space of what does it mean to build tools for dynamic languages, because they really do have a different flavor than the static languages. With that, take some questions. Yeah? Could you say that again, please? Yeah. Deops. Yeah. Same thing, yeah. So you basically, when you switch the value of that enabled flag, which is compiler final, then you create a new assumption that says that it hasn't changed. And then when you change it, then you kick that tire again, and then deopt happens, and you go around the same cycle. That's exactly right. Yeah. Any other questions? Yeah, please. Yes. I have not implemented conditionals yet in the general framework. In the Ruby framework, yes, and the performance numbers are very good. And here's how it works. In the Ruby prototype, you type in a script, really, which is Ruby code. It gets turned into what's called Ruby proc, so think AST. We build a Truffle AST for it. And then that Truffle AST gets glued in to your breakpoint object. Now, your breakpoint object, by the way, is a Truffle node. That's the point. The probe, the wrapper is a node, the probe is a node, every instrument is a node. So they all are subject to full Truffle optimization. And if you glue that conditional AST onto your breakpoint now, it really, essentially, you have rewritten the program. And at that point, eventually optimization will kick in, and all the same optimizations will happen, and it'll run in the fast path with no overhead beyond the cost of the expression in the guest language. It's important that it's expressed in the guest language, because that's where all the optimization work has already been done, and the conditionals then will run as fast as any other expression would. Yeah. Okay? Other questions? Yes, please. Have thought about it, but it's pretty far down the priority list right now because it's still a science experiment. Yeah, to do so would be a kind of a product-ish kind of decision strategy to say, well, yeah, because it's in principle doable. The question is that what we want to do for our purposes right now? Yeah, great question. But we're still a lab project, and so we don't have to think too hard about that yet. Yeah, other questions? Okay, thank you for your attention. Again, I'll be in the workshop. If you'd like to come see the command line debugger run or chat about it or talk about other ideas, please join us. Thanks very much.